A drawback of covariance, which we derived in the preceding video, is that it confounds the relative scale of two variables. So in this case, our two variables x and y. So it confounds the relative scale of the two variables with a measure of the variable's relatedness. So the more that our variable x and the variable y aren't in the same, don't have the same kind of mean and variation, if they're on different kinds of scales, the covariance the calculations will start to get pretty wonky. So correlation builds on covariance and overcomes that drawback of covariance via rescaling, thereby measuring relatedness exclusively. So we rescale with the terms in the denominator here, which I'll explain in 1 second. So correlation is much more common than covariance because of this controlling that we do. The correlation coefficient, which we symbolize with the Greek lowercase letter rho here, so it looks a lot like a p, but it isn't a p, it's a rho, R-H-O, and this correlation coefficient between two variables, in this case x and y, which we show in subscript, it was developed by Karl Pearson in the 20th century. Though it was known in the 19th century, it was popularized by Pearson in the 20th century. So we talked about him earlier on in these live lessons. We actually had a photo of him on one of the slides when we were talking about the history of frequentist statistics. So to define the Pearson correlation coefficient, we take the covariance that we already calculated earlier, and then we divide by the standard deviation of x multiplied by the standard deviation of y. You'll also note here that up on the whiteboard, I was previously showing our measures of dispersion. Anytime that I had the Greek letter sigma, I was showing it in blue, but I realized that I usually always have y in blue, and I didn't want to have, that would have been confusing to have sigma and y in blue here, and so I changed sigma to brown a little bit retrospectively, but I hope you'll forgive me. Okay, so let's work through some real numbers to get a sense of how the Pearson correlation coefficient is calculated. Not just get a sense of, I mean, see exactly how it's calculated, and then develop an intuitive understanding of what it means. So here's the formula from the whiteboard. We have our covariance between our variables x and y. So we're going to use the same ones that we were recently using here. So, if x is sepal length and y is sepal width, then we know that the covariance from the preceding video is negative 0.04. So we can use that covariance again here. So this is where the covariance matrix comes in handy, because it does also have the variance of x and the variance of y, right? So we have the variance of x and the variance of y, which we can now convert quite quickly into the standard deviation of x and the standard deviation of y by taking the square root. So that's something that we've talked about already in these live lessons. If we want to get from variance to standard deviation, we simply take the square root of the variance, and that gives us our standard deviation. All right, so that's about it. We now have everything we need for this formula. We've got our covariance, and we've got our standard deviation of x and standard deviation of y. So we can simply now put covariance in the numerator and divide by the product of sigma x and sigma y. And that gives us a Pearson correlation coefficient of negative 0.12. The added benefit of this relative to covariance is that we're now controlling for the differing variances of our variables x and y. So these differing variances no longer have an impact on our measure of the relatedness of x and y. Now, as is often the case lately, you don't need to do all of these steps to figure out the Pearson correlation coefficient. For example, built into the SciPy Stats module, we do have this Pearson R method into which we can simply pass our variables of interest, in this case sepal length and sepal width, and calculate the Pearson correlation coefficient. We get the same value as we did doing it quote unquote manually. And so the second value output here in this tuple, that is a measure of statistical significance. So that tells us something that we're not quite ready for. We have more to cover, so we will get into that later on in these live lessons when we start talking about statistics and statistical significance. But for now, we don't need to worry about this. All we're interested in is this Pearson correlation coefficient, which is the first item in the tuple. We can access it with this here. So, we can get that number out by asking for the first item in the tuple. And so, so we see that we have this very slight negative correlation between sepal length and sepal width. It's so slight that it might not be statistically meaningful. And we also have, if we go back to the earlier example, so we just calculated the correlation of the relationship between sepal length and sepal width. But what if we go back and calculate the correlation between sepal length and pedal length? So I assume, it looks pretty clear that we have a strong positive correlation between those two variables. Let's confirm that that's true by calling this Pearson R method and passing in sepal length and pedal length. And yes, we get a very strong positive correlation. So the strongest correlation possible is 1. So these Pearson R values, they vary from -1 up to +1, where 0 would indicate absolutely no relationship. So note that these metrics that we've covered, covariance and correlation, they only account for linear relationships. So if two variables were highly non-linearly related to each other, so they had some kind of parabolic relationship or something, or exponential relationship, these metrics could come out as having 0 covariance or correlation, even though that non-linear relationship is there. So just a limitation here of these methods that you should be aware of.